So here we're asked to prove the identity. And the typical way to do that is to manipulate the left and or the right side to show that there's an obvious reason that they should be equal. Put a question mark there. All right, so let's see. Some things I like to do with these is usually if there's anything but sine and cosine, I like to get rid of them. So I'm going to rewrite tangent of 2x as sine of 2x over cosine of 2x. Next, let's see. Could I do more with the left or right sides? Well, we have 2x's on one side, we have x's on the other. That's a problem. Sine double angle. What is the sine of twice an angle equal to? I believe I can rewrite the numerator as, holy shit, that's already up there. 2 sine of x, cosine of x. Okay, so my numerators are equal. This identity is true if the denominators are equal. Thinking about the cosine of 2x, we have 3 versions of that identity. And that right there happens to be one of them. Yeah, cosine of 2x can be written as twice the cosine squared of x, then minus 1. Boom, we are done. This is one possible formula for double angle for tangent. There's many. Yeah, so these, to prove the identity type thing, somehow we have to justify that the left side and the right side mean the same thing. And usually it's getting to a point where we say, oh, right, yeah, I know this equals that, by rewriting and using some other identities. All right, so that one was deceptively easy. Let's see if we can find a harder one. Try 33. All right, so there's another prove the identity. So somehow these two should be equal. Let's see, what do we know about these? Now, I'm a little hesitant to rewrite the tangents as sine over cosine, given that they're squared in top and bottom. That's a possibility. Oh, 1 plus tangent squared of an angle. That sounds familiar. Is that Pythagorean identity for tangent? What's that equal to? That's the secant. Okay, I'll take that. That's a little simpler. Now, it'd be nice to cancel the tangent squared, but we can't because the order of operations says we have to add or subtract before we can divide. So we can't just cancel something. But I do notice that that right there is Pythagorean identity for tangent squared, which is equal to the secant squared of alpha. And let's see, what do we know about secant squared? Or secant? Secant's 1 over cosine, right? Yeah, so we could rewrite the right side. I'm stuck at the moment with 1 minus tangent squared of alpha. The numerator can be written as secant squared or 1 over cosine squared of alpha. Oops. And then I could multiply that into the top, right? Instead of dividing by 1 over cosine squared, I could multiply by cosine squared. So this would be parentheses 1 minus tangent squared of alpha times cosine squared of alpha. All right, well, now I don't have a denominator, so I'm gonna count myself better off. And again, playing with these identities, I often go down paths that don't lead me anywhere and I gotta start over. So this may or may not be productive, we'll see. Well, since I have alphas on one side and 2 alpha on the other, shouldn't I use the double angle? And we have a bunch of different versions of that. So let's look back at the double angle versions of cosine to figure out which one we might want to adopt. Scroll through the book till I get to it. It's at the beginning. All right. One of those might be handy here. Over here. Okay, cosine squared. So I'm thinking one of the ones with a cosine squared might help. Do I really want to introduce a sine squared also at this point? I'm leaning toward the third one. What do you guys think? And again, I could be wrong, and then I'll go back and try the first one. So just try something. So I'm going to rewrite that as twice the cosine squared of alpha minus 1. And I think I feel compelled to distribute on this side. So on the other side, I'm going to have cosine squared of alpha minus tangent squared alpha times cosine squared alpha. All right, we're getting someplace. Suggestions?
Would you divide both sides by 2?
I don't think I'm ready to divide by 2 yet because there's only a 2 here and not anywhere else. So I think I'll leave that for now. But I've got cosine squared hanging out on each side. I could say subtract the cosine squared. So if I did that, minus this cosine squared of alpha over here, minus cosine squared of alpha, that gets rid of the 2. So I'll just have a cosine squared of alpha minus 1. On the other side, I've got cosine squared minus cosine squared is gone, so I just have minus tangent squared of alpha times cosine squared of alpha. Maybe it's time to think about tangent as sine over cosine. Oh, that actually is not a bad idea, right? If I rewrite tangent as sine over cosine, I think I'll get some cancellation. So negative sine squared of alpha over cosine squared of alpha times cosine squared of alpha means I get to whack some stuff, right? Cosine squared of a cosine squared is 1. And this is starting to look promising. What's left? Cosine squared of alpha minus 1 equals negative sine squared of alpha. What do you think about that? Kind of looks like a Pythagorean identity. I add sine squared to the right and add 1, other way around. Add sine squared to the left, add 1 to the right. That's Pythagorean identity. So it looks like this is cosine squared of alpha plus sine squared of alpha equals 1. Yes, that is true. I did some crazy stuff to get there that I think was all legal, which means the original must be true too. Is there an easier way to do this? Maybe. There's probably 10 different ways to do this at least. Again, the goal of proving an identity is start something that you don't know is true and apply some identities you do know to see if you can turn it into something that you know is true. All right, so I could even take this one step further. Cosine squared of alpha plus sine squared of alpha is always 1. So in the end, I pretty much have 1 equals 1, which is true for any angle alpha. That was wild ride. Now, reminder, often when I do these, I do get dead ends and I just have to put my paper away and grab a different piece of paper and try again.